Good morning, students. In the previous session, we were talking about pattern allowances, and we have taken different allowances such as shrinkage allowance. Let me explain once again the shrinkage allowance concept. We were considering temperature and shrinkage graph, that is temperature versus time graph. So here it has got three different segments. The first one is liquid shrinkage, second one is solidification shrinkage, and third one is solid shrinkage. So here for liquid shrinkage and solidification shrinkage, you can provide allowances with the help of risers, whereas in the last segment, that is in the solid shrinkage, you must provide allowances on the pattern so that you can compensate the difference associated with the pattern. Okay. So that is what the concept of shrinkage allowances. We have taken the different materials as examples, and we have explained and we have discussed aluminum, brass and iron as the examples for the better understanding of shrinkage allowance concepts. Then that was followed by machining allowance. Here in the machining allowances, that permeability concept come into picture. So once you take out the product and due to poor permeability of the sand, so that leads to poor surface finish, then we cannot accommodate that particular cast to the further process. For that, the metal cutting come into picture, where you can cut the cast and you can get a required shape or required dimension. For that particular process, you need to, or one has to provide machining allowances. So we have taken the example and we have provided the dimensions and allowances, and this is how one can understand the machining allowances. The next allowances is draft allowance. So here the theme behind this draft allowances, we must provide allowances on the pattern to facilitate the easy removal of the pattern from the mold, and it does not damage the mold cavity. So for that particular purpose, we need to provide allowance. Say this is what the product we required. Okay. So here the draft allowances at the top of the surface, you can provide 2 millimeter per 100 millimeter length. Okay. For if you want to manufacture a square metal casting, so you need to provide 2 millimeter at the top per 100 millimeter length, and subsequently you need to provide 1 degree taper, so that you can easily take out this particular portion from the mold cavity. After that, you can machine this allowances, and that leads to cast. Okay. If this allowances did not provide, then that leads to the distortion or the breakage of mold cavity. Okay. For that, the draft allowance is required, and that is essential also. The next one is distortion allowance. Distortion is basically, the meaning of distortion is the process of losing the shape, that is called distortion. So in order to compensate the lose in shape, we must provide allowance. Say for example, if you want to manufacture the intricate shapes or the the letters like U, L, T and all, so it has got some different contours. Say for example, this is the U, that is the shape of the cast we required. Okay. So here this is the pattern we have provided. In the solidification process, there is a obvious thermal stresses come into picture. This particular thermal stress is acted on the wall of this particular pattern, that leads to the distortion in shape. So this is what the cast you would get when you have not provided the allowances or without allowances. So due to thermal stress associated in the solidification process, so this particular U shape is distorted into, or this leads to widening the gap in this particular letter. So once you provide the allowances in the opposite to the expected distortion, so this is the distortion expected, okay, in this particular direction. That's why we have provided the allowances in the just opposite to the expected distortion. Then finally you would get the cast of the appropriate shape. That is the concept of distortion allowances. This is without allowances and with allowances. So, you need to concentrate on the direction in which the stress is being acted on the wall, and that leads to distortion. So, in order to avoid this particular distortion, so you must provide the allowances just opposite to the expected distortion. Finally, that leads to a perfect cast. That is the concept of distortion allowance. The next concept is base sand or mould sand. So, this is the definition of base sand is, this is the mass of refractory grains without any ingredients. So, here the ingredients such as additives, binders, okay, these are all the ingredients of this particular sand, but we are not considering any binders or additives. I will let you know what actually the properties and significance of having binders and additives in the next in the coming session. So, let us take up this base sand concept, that is the mass of refractory grains without any ingredients, that is called base sand. So, this particular sand is put it into a cope and drag back boxes, then you can have pattern, just you ram it, then you take out the pattern, then that leads to cavity, that is called mould cavity. Okay, for that particular process, this sand is a predominant requirement. So, here we are considering the mass of refractory grains without any ingredients. Here some examples are silica sand, zircon sand and chromite sand. These are all the different base sands without any ingredients. Then what are all the requirements of base sands or properties that should possessed by this base sand? The first property or requirement is it should have higher refractoriness. Why it should have the higher refractoriness? Because if you pour the high melting temperature, high melting point metals into the mould cavity, then that can easily accommodate or receive that particular temperature once it possesses higher refractoriness. The next requirement is thermal expansion. So, here once you pour the hot metal into the mould cavity, then obviously it has to withstand the high temperature, otherwise that leads to the fuse of different sand particles. Then obviously permeability becomes low, then if the permeability is low, then that eventually leads to the poor surface finish of the cast. So, for that particular cast, the secondary process is demanding. To avoid such consequences, we must provide or that particular base sand possesses thermal expansion or lower thermal expansion. The next property is chemically it should be inert. Okay. Then the next requirement is it should possess high permeability. As I said earlier, permeability is the ability of a sand to let the hot gases or the gases out of the system. That is called permeability, that can permit to go or that is going to permit the hot gases get out of the system. Okay. Then the next requirement is it should have low impurities. As the impurity increases, then that leads to the reduction in the quality of the cast. Then next one is good grain distribution is required. Then good cohesiveness is demanding. Then flowability, the flowability of sand. You are not we are not talking about the flowability in terms of fluids. I am talking about the flowability of sand. I can define the flowability as this, the ability of a sand to move each and every or nook and corners of the contours of a pattern, okay, when the ramming process is taking place. Once again I will repeat, flowability is the ability of the sand that can move to the every corner of the pattern, okay, then when the ramming process is taking place, that is flowability. For this particular base sand, it should have higher flowability. Then the last requirement is collapsibility. So, base sand should possess higher collapsibility. So, here in the collapsibility is the ability of the sand that can easily you can collapse the mould box or the mould sand. Okay. So, that is the requirements of base sand. Once again I will repeat, it should possess the higher refractoriness and it should have the low thermal expansion, it should have chemically inert and high permeability, and it should possess low impurities and good grain distribution, then good cohesiveness and flowability of the sand should be high, then collapsibility of the sand should be high. Okay, these are all the requirements. The next ingredient is binder. Binder, as the name indicates, that is one more ingredient that is being added to the sand to impart cohesiveness, or the bind is a basically binding agent that is going to bind the sand particles. So you have got different or two different types of binders, that is organic binders and inorganic binders. So example for organic binders are mineral oil and linseed oil, whereas in inorganic binders we have a fire clay. Okay. Next segment is additives. Just now we have discussed about binders, and the next segment is additives. These two are the ingredients of mold sand moulding process. So the additives are the basically materials that is being added to the sand mold in order to incorporate the new properties with the existing properties. Say for example, we have different additives, that is silica flour and wood flour and sea coal and iron oxide. Okay. These are the different additives, and why we must add these additives to sand moulding technique. So the significance behind having silica flour is to reduce the thermal expansion property, and that would provide the thermal expansion property. Then if you add wood flour, that enhances the collapsibility property of a particular sand. Then for sea coal, you can have better surface finish of the casting. Then similarly in iron oxide, that can enhance the strength, hot strength of a particular sand moulding techniques. So these are all the ingredients of base sand, that is binders and additives. Then next concept is different sand moulding techniques. So once again I will make it clear. Sand moulding is the process of making a cavity using pattern. So process of making the mold cavity, that is called sand moulding techniques. We have got different sand moulding techniques, that is green sand mold technique, dry sand mold technique, then core sand mold technique, then sweep mold, followed by carbon sand moulding, carbon dioxide sand moulding. Let us look into the first one, that is green sand mold. Green in the sense that is moisture content. This sand, that is, it has got some moisture content, that is called green sand. The ingredients of this green sand is, so by percentage of volume you can calculate, that is silica has got 85 to 92% of volume, then binder 6 to 12%, then water 3 to 5%. So you can you put together within that particular cope and drag boxes, then you can have the pattern and core. Once you take out these core and pattern, that leads to the formation of cavity or green sand mold. For this is a place where you can pour the hot metal, then after solidification process you can take the product. Then what would be the application of this green sand mold technique? So you can have the axle housing, or you can manufacture axle housing with the help of green sand mold technique, or you can manufacture motor casing, then flanges, manufacturing of flanges and railway bogies. These are all the different wonderful applications of green sand mold technique. Whereas the next concept is dry sand mold technique. In dry sand mold technique, the composition remains same, but we are heating the this sand with 6 to 12 hours with 200 to 300 degrees Celsius within the oven, in order to remove the moisture content associated with this particular sand. That is called dry sand. Okay, the process remains same. Again, you can have pattern, core and vent, sprue. These are all the different terminologies or elements of this casting process. Just you take, after you can pour the molten metal, then after solidification you can take out the product. The difference between green sand and dry sand is there is no moisture content that is associated within the sand before pouring the molten metal. That is the concept of dry sand. Whereas in green sand there must be a moisture content before pouring the hot metal into the cavity. That is the main difference between green sand and dry sand. The next concept is core sand mold. Why we should call this particular process as core sand? Because here a core sand mixture is being used to manufacture this particular one. So here the composition is base sand plus core oil binders. As I said earlier, the function of the binder is to fuse the sand particles together or to impart some cohesiveness among the sand particles. Then here you can assemble different cores to the required shape, and we can eliminate the patterns, then you can get the shape of a mold cavity of our choice. Okay, that is the with this is all the backing sand, and this is the core. We have considered different cores and assembled together to get the required shape, and finally that leads to cavity. Okay, for that particular cavity you can pour the hot metal, solidification, again cast you are getting. Okay, that is about the core sanding molding process. Then the next molding technique is sweep mold technique. So sweep mold technique, here you have got this setup, that is it has got different elements, that is spindle, and spindle is attached to a wooden board, and the next one is you can place the spindle centrally to the cope or drag boxes. Then you can slowly rotate this particular spindle is attached to this wooden pattern, then you can expect a symmetrical or circular shape. Okay. So loosely you can pack the sand, then you rotate this particular pattern slowly with low RPM, then that is going to sweep the sand, then that leads to the formation of circular or symmetrical shape. So that is the concept of sweep mold. Then the next concept is carbon dioxide sand molding technique. So here this setup remains same, that is as usual cope, drag, pattern and sprue. These are all the vent, these are all the different as usual setup. For that we are supplying carbon dioxide gas. Why we must supply carbon dioxide gas? Because that is going to react with sodium silicate. That is here, this is a chemical reaction taking place here, that is sodium silicate combines with the carbon dioxide, that leads to sodium carbonate plus silicon dioxide, then that leads to silica gel. This silica gel is going to bind the particles of the sand. Okay. Once the binding process is good, obviously you can expect the high strength and low permeability, and you can have better properties associated with this particular sand. That is why this carbon dioxide is being added to the existing sand, then because of this chemical reaction you are getting, or that leads to the formation of gel. The function of the gel is to bind the particles. This is what the concept behind carbon dioxide sand molding technique. As of now we have discussed about different sand molding techniques where you can have different ingredients like sand, binders and additives. Then that leads to the generation of a particular mold or mold cavity. To that particular cavity we can pour the hot metal and you can get the desired shape after the solidification process. This is what the concept of casting process. So here we have discussed about green sand mold technique, dry sand mold technique, carbon dioxide mold technique, core mold technique. Then the one more technique is the next technique is shell molding, then investment molding and plaster molding techniques. So let us understand the shell molding technique. So here this drawing depicts the process or the sequence of operation to be performed in order to get the cast. So here the first step is, here this is the metal plate. So this metal plate is attached with the pattern. Okay, the pattern is heated to about 200 to 250 degrees Celsius. Okay, so this is the dumping chamber for which we have to put resin and sand mix. Okay, upon inverting this particular dump box, then this mixture is fell on this heated pattern. So this resin come in contact with the heated resin, heated pattern, then that leads to the formation of a thin layer. Okay. So the thin layer of sand is formed on the existing heated pattern. So that leads to the formation of green shell. Okay. Then This particular green shell is cured above 300 degrees Celsius, so that we can take out the moisture associated with the green shell. So that leads to hard shell. Okay. The next step is you are joining these two shells, two halves. Okay. So that leads to the formation of this particular structure where you can have a molten metal. Okay. So this molten metal, after solidification, you can detach these two, and that leads to the formation of a cast or a casting process. Okay. This is what the concept of shell molding techniques. So here the shell molding, why we should prefer shell molding process, because you can have the product with higher dimensional accuracy, then you can have a good surface finish, and productivity of this particular process is very high when compared to other traditional molding techniques like green sand molding or core sand molding or some carbon dioxide molding and all. Okay. The next one is, then you can manufacture different components with this particular process. Okay. Say for example, levers, gear levers and casings, and some automobile parts can be manufactured with this shell molding techniques. The next molding technique is investment molding techniques. Why we must term this particular process is called investment molding. Investment, the term is derived from the fact that we are investing the patterns. We are investing the wax patterns during this particular process. That is why we must call this particular process as investment molding techniques. So this process starts here. Here this is the component, this is C, or the English letter C component is required, say for example. Okay. So you have, if you want to manufacture more and more with a small scale components, you can have 2 or more or 5 to 10 different patterns of the required shape. Then you can make the cluster of this and establish sprue, runner, gating and all. Okay. Then you can dip this particular wax pattern or cluster into the slurry. Slurry is made out of some different refractory grains. Okay. Then you can pour a you can spray the sand grains, and that leads to the formation of shell. Okay. So this, the next step is you heat this particular structure above 1100 or 200 degrees Celsius. Then that leads to the flow of wax. This is where the wax is invested, and it could be reused and it could be reinvested in the next process or the next cycle. Then the next step is here you have got you can pour the once you get the appropriate structure, then you can pour the molten metal into these particular cavities. Then after the solidification process, you can detach it and you can separate it, and you could get the different number of the casting, that is what the component required. Okay. This is what the concept of investment molding process. The next one is plaster molding. So here in the plaster molding, this particular molding is meant for only for non-ferrous castings. So say for example, this is most preferably used for aluminum alloys. Okay. So you cannot have, or you are not supposed to have high temperature alloys like nickel, chromium. These are all the very high temperature alloys. You cannot use these particular alloys for this particular molding technique. This plaster molding technique is only meant for non-ferrous casting, preferably for aluminum material. Okay. Then say this is the process explanation, that is, this is the plaster of Paris is mixed with the water. Then you can have the slurry of the plaster of Paris and water. Then if you eat it, then this particular slurry is poured on the pattern, that is existing pattern. Then that takes the shape of the pattern. Then you can allow to cool. Then you can get this setting of the plaster of Paris. Then you can remove the patterns. Then you can have the mold cavity. For that particular mold cavity, you can pour the metal of your choice or the non-ferrous alloys. Then after solidification, you can get the particular cast. So the next topic is molding machines. So as of now, we have studied different molding techniques such as dry sand, green sand mold technique, carbon dioxide mold technique, plaster of Paris mold techniques, shell and investment molding techniques. These are all the different varieties of molding techniques, where we were using hand tools to ram a particular ingredients into the pattern to get the desired shape and to get the casting process done. So here, in order to have a uniformity among the compaction of the sand and a faster rate of molding, we can eliminate the hand mold tools and human intervention. We are considering the machines called molding machines. So we have got different types of molding machines, that is jolt type molding machine, squeeze type molding machine, then slinger, sand slinger type molding machines. So the intention is very clear. We want a good quality of mold. Okay, that could be achieved with the molding machines instead of human labor. Okay, here this particular diagram shows the working principle or the structure of this particular machine. So it comprises of piston and cylinder arrangement, and it has got two slots, that is the wall 1 and wall 2. This is the pattern, and these are all the sand with the ingredients. So here through this this particular wall, the compressed air is passed, and that leads to the upward movement of the piston. Okay, that leads to then this compressed air is elevated this piston up till here, then the compressed air is going out of the system, then by the virtue of its weight or the gravity, that is coming down. So going up and coming down, that leads to some pushing action. So this particular push or the shake process is called as jolt type. Okay, jolt is in the sense that is you can push or you can jolt. Okay, so here from that particular jolt action, this particular mold box or this particular ingredient is come in contact with the pattern, then that leads to the strong adhesion of the ingredients on the pattern. Once you remove the pattern, you can get the good quality of the molding. Okay, so let us talk about the specification of this particular type. So you can have the table size of 750 into 650 into 200 millimeters. I have taken the example, that's it. Then the jolt capacity is about 5000 Newton or 1800 degrees or 1800 Newton. Okay, this much of force is required to create the jolt action in this particular process. So the next one is squeeze type molding process. As the name suggesting that we are squeezing the sand ingredients or base sand and its ingredient to get the quality mold with a very minimum amount of time. So here again it has got the same elements of the machines. So we are replacing two walls with the two-way control valve. Okay, through this two-way control valve you can send the compressed air, and again this compressed air is elevate the table to the next level. Then this particular board is compressing from the other end. So pressure is being acted from the downward as well as upward. Then that leads to the compression in this particular one or squeeze of the particular sand and its ingredients. Then in turn this will provide a perfect platform to have the good quality of mold. Okay, that is about squeeze type. If you talk about the specification, again the table size is 750 into 650 into 200 millimeters. We must talk in terms of volume. Then you can have the squeeze pressure of 0.3 Newton per millimeter square. That is the intensity of pressure is required to get the desired quality of the mold. Then the next molding machine is sand slinger machine. Slinging or slinger in the sense that is you can throw something away with very good velocity. So here this is what the pattern. Okay, this is what the mold box. The intention is to fill the mold box. Okay, so we are using this slant slinger machine. Okay, this machine is capable of throwing the ingredients with a higher velocity to fill this particular mold box. That is the intention. So here this is the sand container with appropriate ingredients. Okay, it has got a pulley and drive, and this rope is connected with the buckets, and that can take out the sand and its ingredients, and that is elevated to some level, then that is push it on to the hopper. From the hopper with the higher velocity, that is going to feed the sand ingredients, and that leads to the perfect compacting of the sand and its ingredient on the pattern. Okay, then once you remove the pattern from this particular mold box, that leads to a good quality of a cavity. Okay, then that cavity could be used for the casting process. That is what the concept of sand slinger machine. So the slinger capacity is about 5 meter cube per hour to 15 meter cube per hour. Okay, that is the capacity of the sand slinger. Okay, then box size is of 800 into 800 into 600 millimeters. Okay, this is what the specification of slant slinger machine. If you want to have a mold with a very big volume, you can prefer slant slinger machine instead of these two machines. This is what the concept of different sand molding techniques or the sand molding machines.